Hello, we're Group 7 and we've chosen to do the range equation for ballistic motion. The range equation is here, and now Brandon's going to tell us a bit more about that.
First things first, we had to look at our first experiment where we calculated the average distance. We did 6 trials and the average distance traveled was 26.5 feet. Shebang. The height we knew was 3 feet, and with that we could solve for time using the kinematic equation in the y direction. And we did that and we solved for time equals 0.435 seconds. That sounds better. Boom. Checkmate. And then, now that we know time, we can solve for the velocity is 60.92 feet per second using the kinematics in the x direction. Then we have to derive the range equation. This derivation's a little messy, so we're going to go through it really fast here. But it's basically a derivation that involves the kinematic equations in both the x and y directions and the associated angles. And as you work through it, with gravity and the velocity initial, you solve for range is equal to the velocity squared cosine theta over g times sine theta plus or minus the square root of sine squared theta plus 2 height g over velocity squared. Basically, it's pretty simple. We used the Nerf gun as a kinematic launcher. We got the velocity of the bullet, and then once we knew the velocity, we derived the range equation, which we can then manipulate at any angle or height we want to solve for how far the bullet's going to go and where it's going to land in these targets.
So for this experiment, we're using a spring-loaded Nerf gun to shoot our bullets and a protractor, which helps us get the angle that we need so we can determine the range. We're also using a tape measure to measure the distance, provided by Shell, very kindly of them, to get our distances that we need.
We're obviously not working in a vacuum here, and so we have to factor in some air resistance. And so we figured the air resistance would affect the range by about plus or minus 5%. And shooting from there down to here is about a 60-foot range, so about plus or minus 5% should be about 3 feet on either side. So we've got this box here to kind of catch that error range.
So basically, we've got a 3-foot step tool up there, and then we clamp this down and we lock it into place, and we've got the protractor for the angle. That way we're guaranteeing initial height, initial angle, and distance.
The setup for this experiment involved using a ladder and a clamp to keep our gun at our 3 feet height and 15 degrees. We then placed a box 67 feet away, which is what we got for our range by using our range equation that we derived. It had a uncertainty of about 3 feet in either direction. Because of air resistance, we figured that there would be a 5% uncertainty. Firing. Alright, firing. Hey! The laser rangefinder is the best example of using the range equation in the real world. It works by shooting a laser with the known velocity of the speed of light at a target. The device times how long it takes the laser to rebound back to it. Using all of these known quantities, the rangefinder is programmed to tell the user how far away the target is. Laser rangefinders are mostly used in military and hunting applications. Soldiers and hunters commonly use these to help figure out how far away a target they are trying to hit is.
From here, we put in different angles and velocities into MATLAB to judge where the dart would go before we made our trick shots. Oh! Alright, you good? No.
Target acquired.
Oh my god!